Hello and welcome to another OPAL-RT Learning Journey presentation. This is a survey of OPAL-RT electric machine models. I'm your presenter, Brian Kindiger, and I am a software engineer at OPAL-RT. So our objective is to explore the commercially available electric machine models that are created and maintained by OPAL-RT. To do that, we're going to be discussing first, the applications and industries that would be interested in electric machine models. We'll be talking about the general considerations and constraints when thinking about electric machine models, as well as we'll be talking about my product, which is the Power Electronics Add-on for NI VeriStand. We'll be going over what a full simulation system is made up of, both the hardware and the software. We'll do a few demos, and then finally we'll wrap it up by going into kind of a little bit more detailed perspective of each of the machines that OPAL-RT has as off-the-shelf models. In the end, we'll provide some links and some next steps so that you can learn more about OPAL-RT models and products. Who is the primary audience for this presentation? The answer is scientists and engineers who are trying to test their electromechanical systems faster and cheaper than previous historical methods. Since there's been an explosion in technology related to electrification in many industries, the amount of companies investing in hardware-in-the-loop programs is rising quickly. This obviously includes the automotive industry, but electrification is starting to be a large topic in other industries such as avionics, as well as alternative energy sources like wind and solar. All of these trends are opening up opportunities for hardware-in-the-loop, and most require some sort of electrical machine to be simulated. So what do we care about when it comes to evaluating electric machine models? In general, there are four primary concerns. The first is relevant for all modeling applications: modeling fidelity. Model fidelity is the degree to which a model or simulation reproduces the state and behavior of a real-world object. Model fidelity is a subjective way of saying, how close is my electric machine model to the real electric machine? Model fidelity can be broken into accuracy, which is essentially looking at how similar the governing equations of the model are to the real machine. It can be broken into speed, which is a measurement of how small of a time step the model can be executed in, and determinism, which measures how much error in the time step occurs with the specific model. Because we want a small time step and low jitter, it makes sense to implement models on FPGA targets with dedicated hardware to do the math. A question we also get a lot of is if our machine models are 4-quadrant. 4-quadrant simply means that the motor can rotate clockwise and counterclockwise, and that power can be absorbed by the machine, and the machine can also push power back to the inverter and to the battery. Sometimes you'll hear the term motoring and regenerating. Motoring means power is being pushed from the battery to the machine, and regeneration means that the power is being returned from the machine back to the battery. All of the models that we'll be discussing today are 4-quadrant, so they can go forward, backwards, and regenerate and motor. Since we implement the machines in FPGA to meet our model fidelity requirements, it also means that the models need to be highly configurable so that we don't have to waste a lot of time recompiling models for FPGA targets. The final one is simulated sensors. So all actual machines have sensors for the controller to read and then react to. And so in this way, we have machine models that are integrated with our sensors. And the three most common sensors for electric machines are quadrature, encoder, Hall effect, and resolver. Now, not every type of machine uses all three. Typically, they'll use two or one of them. But in general, all of the machines already have these sensors integrated into the machine itself. We're going to be looking at two software products today. The first is NI VeriStand, which is a software platform that enables users to more easily integrate NI, OPAL-RT, and third-party hardware into a hardware-in-the-loop solution. Second product is the OPAL-RT Power Electronics Add-on for VeriStand, or just the Power Electronics Add-on for short. The Power Electronics Add-on is a VeriStand custom device which executes OPAL-RT solvers on the NI platform. It provides an intuitive UI for configuring models in the VeriStand system definition. The data generated from the models is exposed to the user through VeriStand channels and waveforms. If none of this makes sense to you, that's okay. We're going to have some demos that are going to try to make it a little bit clearer. Let's go ahead and get ourselves oriented. I've gone ahead and diagrammed a simplified HIL solution. On the right-hand side, we have our device under test. This would be something like your car's ECU, or an inverter controller, or even a wind turbine controller. It connects to the real-time simulator, typically through some signal conditioning and fault interface. Here I have a DUT connected to an SLSC chassis. SLSC stands for Switch Load and Signal Conditioning, and is a hardware platform with many types of channel options. After signals are conditioned, they are passed along to the FPGA instrumentation. In this diagram, the electric machine models are compiled into an FPGA bit stream and then loaded into the FPGA at execution time. Since the FPGA is reprogrammable, we can support multiple types of machines simply by downloading different bit streams depending on the application. Here we have a PXI chassis with FPGA boards already connected. The FPGA cards then connect to the controller, sometimes called the CPU, which runs a real-time operating system. The CPU can run slower models, communicate data to and from the simulator, and executes additional needed functionality. All of this data is then communicated back and forth from the operator interface, which displays it through a customizable VeriStand UI. I've prepared two demos for today. They are both similar and simple, but they should give you a good idea of the workflow. The first demo is an example of controlling a machine using a software model executing on the CPU. The software model is specifically an implementation of a volts per hertz controller. Since the machine is not being controlled by an external piece of hardware like an ECU, but instead the simulated controller on the CPU, this would be more accurately described as a model-in-the-loop type demo. The specific machine I will be controlling is a permanent magnet synchronous machine, and I have configured it to have constant LD and LQ values, and we can talk more about what that looks like later on. The volts per hertz controller outputs IGBT signals, which interact with a circuit being modeled on the FPGA, and this specific circuit is simulating the battery and the inverter. That model in turn provides the PMSM model with voltages. Then the PMSM model solves for currents, which are then fed back into the circuit model. And then finally, the circuit model provides the necessary feedback back to the controller so that it can complete its closed loop control. The end result is a fully functioning closed loop simulation where we control the speed of the machine through a VeriStand UI. So I've started the demo by already opening up a shipping example with the Power Electronics Add-on. The particular shipping example is the dual PMSM VDQ local control example. To get started, I'm going to go ahead and open up the system definition, or sysdef. If you're unfamiliar with VeriStand, the sysdef is the way that is the view that the user uses to configure their system before they start the execution. Now that the sysdef is loaded, we can see that we have our controller here, which will be executing all of our models. And if I click on it very quickly, this is a FARLAP controller, but we're able to support also Linux RT targets. Underneath Custom Devices, you'll see the Power Electronics Add-on. Now we're going to start exploring the entirety of the add-on, and then we're going to focus specifically on the machine. So the add-on is made up of two parts, the circuit model and the hardware configuration. The circuit model is primarily for configuring all of the modeling elements of the application. And then the hardware configuration section is the interface, the I/O in and out of the FPGA device. So in that way you can kind of think of it as, if you're a modeler, you would probably focus more on the circuit model portion, and if you're the test engineer or the person responsible for creating the connections to the DUT, you would focus on the hardware configuration side. Now I'm going to navigate to the top level page of the add-on, which is located right here. And here you get information about what the current version of the add-on is, as well as what your current hardware configuration you're using. So the hardware configuration tells you how many FPGA targets are in your available configuration, as well as all of the modeling elements that are selectable. So for this dual PMSM VDQ local controller example, we've selected this particular hardware configuration, and then inside of that we know that there's one FPGA target, the 7868R. It has the EHS64, which is a generic electrical solver circuit, which I'll talk more about in a second. It has dual PMSM and BLDC models with encoders, Hall effects, and resolvers. And then it has some signal generators and some scaling options for analog inputs and analog outputs. If we go to the circuit model page, here we see what circuit is going to be loaded into the FPGA when we hit execute. So if you remember earlier, I was saying that the motor model will be reacting to a circuit model in the FPGA. Well, this is where you can actually set what the circuit is. And one of the largest features of the Power Electronics Add-on is that we're able to dynamically load Simulink electrical circuits into the FPGA without having to recompile the bit file. So you can see here that I have loaded a Simulink model file called the PMSM EHS UB model, and I've already gone ahead and opened up Simulink so that we can look at it. And essentially it's a simple two-level inverter with a three-phase rectifier which for power, and then what we're going to be controlling is actually this inverter side right here with these IGBTs, and then those signals then go on to these sources, which are then connected up to our machine model. So that was really fast. If you want to get a more detailed explanation about how this works, at the end of the presentation I have the Power Electronics wiki linked, and it goes into greater detail as to how exactly all of this works together. But the highlight is that this circuit will be loaded into the FPGA beside the motor model, the PMSM motor model. And then we'll use this circuit to drive the motor and control it. Under the circuit model page, we can expand it and see all of the modeling elements that we can configure. So I'm going to focus in on the PMSM model here. And on this configuration page, we can see all the different parameters that are configurable for this PMSM model. We have our phase resistances, we have some phase inductances, some permanent magnet flux, and a pole pair setting. And then on top of that, we can configure what are the voltage inputs into the model. So we had our circuit that had our two-level inverter, and down here this defines how to map that two-level inverter signals to the machine, and then you can map back to the currents back to the circuit as well. And that's how you close the loop with between the circuit and the machine. We can also go down to the second machine, because this is a dual PMSM configuration. There's two of them. And here it's got the exact same settings, and I'm not really using this portion of the machine, but I wanted to show that you can independently configure the two. So now I'm going to go ahead and deploy this configuration. So we can go ahead and hit save. We hit close. And go up here and I hit deploy. And so now it's going through the process of taking all of this configuration information and downloading it onto the controller so that it can start executing all these models and various custom devices, as well as any other third-party software tools that I need to have loaded into the system definition. The deployment typically takes a little while, so I'm going to fast forward just a hair. And the green light up top means that it's now deployed and executing on the target. So now we can open up the workspace. And the workspace is one of the two UI options for VeriStand that you can essentially use to probe signals that are executing in your controller. So I've kind of taken a smattering of signals. So up here we have our inverter phase voltages, so you can kind of tell I'm already sort of applying a small voltage. And then here we have our DC link, and this is the DC link that is being powered by the three-phase inverter, so you see a little bit of ripple there. Then we have the speed of our machine. Here it's sitting around 0 RPM, so it's not really moving yet, but we already have some phase currents, and that's because we're holding the machine still at this moment. And you can look at those currents both in the phase domain or in the DQ domain. Now I'm going to go ahead and give the machine some speed. So I'll set its set point to 1000 RPM. And you can see the machine starts moving. We start seeing our inverter phase voltages. Our currents start looking sinusoidal. And then we reach 1000 RPM. And now focus is back in, and you'll notice that this graph keeps updating to continuously scale. If we don't want it to scale, we could turn off scaling and set it to something fixed like 3000 and 0 RPM, and then I can go ahead and make it go up to 2500 RPM. The point is you have a lot of flexibility and control over a bunch of signals as the model is executing. I'm even able to change parameters of my volts per hertz controller as it's executing. So here I've made it so that there's a ramp rate related to the speed of the machine, and I can actually change how quickly that ramp rate is and then make the machine change its speed much quicker. So it's quite a bit quicker, and then I can make it even larger. And at this point it's trying to change the speed so quickly that you get a lot of ringing when the machine comes up and down from speed. So you kind of get the idea that you have a lot of flexibility in how you visualize what's going on in your models. Let's take a brief moment to go back into the system definition, so you can still look at the system definition while it's executing. And as it's opening up, there's a lot of signals that are available to you in the machine model itself, and we'll go over a bunch of them a little bit later on, but I wanted to show what they kind of look like in the system definition. So if I go under the machine, you'll see that we have all of our phase currents. Our phase currents are some average voltage for the phases, our reactive power and active power, IDIQ, our back EMF signals. And then if we look under the mechanical model for the machine, you can actually see your speed, your load torque, what the mechanical angle is. Essentially, these are all the channels that you're able to visually inspect live data being updated on the controller. The second demo is very similar to the first demo in that we use the same volts per hertz controller to control the speed of the PMSM. But in this demonstration, the PMSM model is a higher fidelity one. The specific name for the model is the PMSM Spatial Harmonic model. The way you configure it is by using high-resolution engineering files from either JMAG or ANSYS to load in precise modeling parameters into the PMSM. The result is a model that reacts much closer to how a real-world machine would. So this demo is another shipping example with the Power Electronics Add-on, and its specific name is Dual PMSM SH Local Control. And you can tell right away that it's very similar to the previous demo, with a lot of similar signals already up on the screen. One of the main differences is that you can start to see the signals aren't quite exactly sinusoidal like the last demo, and that's indicative of the fact that this is a higher fidelity model. I'm going to go ahead and give it some speed. And you can see the machine takes off right away, and then you can kind of start to see that there's more oscillations in the speed. It's not quite as ideal. And that's kind of what I wanted to show off. I'm going to go ahead and close this and disconnect the controller. And we're going to go look at the system definition. So one of the main things that I wanted to take away from the second demo is that even though we've swapped machines, the overall layout and configuration of the add-on is very similar. And the reason why that was done is it makes it so that it's a lot easier to migrate from one model to another. So we still see our circuit model page and our hardware configuration page. And if we expand it, instead of seeing the PMSM VDQ, we now see PMSM SH. And if I click on it, we see different configuration parameters. So with the SH, there's only one major configuration item, and that is that modeling file that I previously mentioned. And so you can see it right here. It has an extension RGT, and this is a JMAG file that has been compiled and then loaded into the FPGA as it was being executed. As you were able to see, sometimes it's difficult to compare models as they are executing because the amount of data at any one given moment is quite high. To help look at the differences in the models, I have recorded some actual data for us to inspect. On the left, we have constant LDLQ PMSM model. You can tell because the solved currents have a sinusoidal shape. That's because we're using constant parameter, which in turn simulates like the machine has perfect magnets. By comparison with the Spatial Harmonic version, we can see portions of the waveform that have distortions. This is much more realistic to how currents are impacted by magnet shape and position. With this level of fidelity, you can start to test how your controller reacts to current harmonics, torque ripple, cogging torque, and saturation. So you may also be asking why someone might choose the lower fidelity constant LDLQ model. Well, a lot of customers like to be able to start with the lower fidelity model since it's easier to configure and stabilize. Then, if they want, they'll migrate to the Spatial Harmonic model when they feel comfortable with the controller's performance and have the necessary modeling files from JMAG or ANSYS. Now we're going to go through each supported machine model one by one. I have up here a tree representing the hierarchy of various types of electric machines. It isn't exhaustive but covers the main machine categories. At the top we separate into DC motors and AC motors. Of the DC machines, there are brushed and brushless. AC machines can be categorized as synchronous and asynchronous, where synchronous includes switch reluctance, hysteresis, and permanent magnet, while asynchronous includes squirrel cage and wound rotor. The boxes in red outline the off-the-shelf machine models currently available from OPAL-RT. The permanent magnet model in particular has 3 variant implementations, each of increasing level of fidelity, whereas the brushless and the squirrel cage only have constant parameter. We'll start with the machine that we already saw in the first demonstration, the PMSM constant LDLQ. This is the lowest fidelity PMSM model variant. It allows you to configure the stator resistances, permanent magnetic flux linkage, direct and quadrature inductances, and the number of pole pairs. I have provided 2 equivalent circuit models to explain what we're allowed to configure with the constant LDLQ. Each stator resistance is able to be set independently and is represented in the phase domain circuit. For inductances, it's necessary to look at the DQ domain circuit model. We won't be going into explaining the DQ transform, but in general, the DQ domain model is an equivalent model that looks at how to represent signals and electrical components in a way that is synchronized to the position of the machine. It looks at voltages and currents that are in phase with the machine, which is represented here in the D portion of the circuit, as well as it looks at currents and voltages that are outside or out of phase with the machine's angle, which is represented down here at the Q portion of the circuit. Many control designers like to think in the DQ reference frame because it provides a simpler way to control torque. As the name implies, the PMSM constant LDLQ model has constants for the LD and LQ parameters, which are configured here, direct inductance and quadrature inductance. Having a constant LD and LQ means the machine operates in an ideal way, and it is not real-world realistic, but a good place to start when testing your controller. The PMSM variable LDLQ model is a medium fidelity machine model. The equivalent circuits are similar to the constant LDLQ, except instead of having constant values for the inductances, they're now variable inductances and are dependent upon the state of the machine. Specifically, how much direct and quadrature current is being generated. We define the parameters with a file called the external model file that follows a defined JSON schema. Essentially, the LD, LQ, and magnetic flux linkage is determined by a lookup table defined by the ID and IQ state of the machine. This picture down below tries to explain what that might look like, but it's essentially a 2D table where the machine is constantly looking at what its current state for ID and IQ is, and then it looks that up and uses that to find what its value for LD, LQ, and magnetic flux linkage is. This entire table is actually loaded into the FPGA so that the values of LD, LQ, and magnetic flux linkage are updated at the speed of the model's time step, which is typically in the megahertz range. Now for the highest fidelity PMSM model, the Spatial Harmonic model. Similar to the variable LD-LQ model, parameters for the Spatial Harmonic model are loaded using a file. You can see right here where that configuration is. But unlike the variable LD-LQ model, this file isn't created manually by a user, but instead by using the JMag and ANSYS tools, or by getting the files from a machine designer. The files generated by JMag or ANSYS are quite large and contain a lot of information, but ultimately we're doing very similar operation as to what we did in the variable LDLQ, which is we are looking up what the parameters are based on the state of the machine. Instead of using ID and IQ to look up parameters, we instead use the machine's angle, the current amplitude, known as I-amp, and the angles of the currents referred to as beta. The end result is a best-in-class model that can be used not just to validate the controller's operation, but also tune parameters without needing a real machine. The next machine is the Squirrel Cage Induction machine. The name Squirrel Cage Induction machine comes from the fact that it induces a magnetic field in the rotor, rather than having magnets created from rare earth metals. And because apparently people like to put squirrels in cages back in the day of Tesla, I guess. Here's the equivalent circuit model in the DQ reference frame. In the Power Electronics Add-on, we're able to configure the stator resistances, the rotor resistances, the stator leakage inductance, the rotor leakage inductance, the mutual inductance, as well as the pole pairs of the machine. An interesting feature of the Squirrel Cage Induction machine is that it has the option to allow for zero-sequence simulation, which is a way to model for imbalances in the machine's voltages and currents. You can see that portion of it down here denoted as optional with a dotted box line. You enable and disable it through a drop-down located right here, And then when it's enabled, you're allowed to set the 0 sequence resistance and 0 sequence inductance. The fifth and final model we will be looking at today is the brushless DC motor. A brushless DC motor, or BLDC, is a synchronous motor powered by a direct current, but which you control by feeding alternating current to drive each phase. We are able to configure the stator inductances, as well as each resistance in each phase independently, the permanent magnetic flux, as well as the machine's pole pairs. Of interest is the back EMF that the BLDC creates. In general, BLDC motors typically have a trapezoidal back EMF, while PMSM motors have a sinusoidal back EMF. The shape of the motor's back EMF is important because it determines what type of drive current and commutation method should be used. You can alter the back EMF by setting the back EMF flat area parameter, located right here, and that changes the number of degrees that the machine produces a flat region for the back EMF, which you can kind of see here in the waveform picture. We indicate that the trapezoidal back EMF with these voltage sources located here in the phase domain current of the model. With that, we're at the end of the road for our survey of off-the-shelf electrical models created by OPAL-RT. I hope you learned about our various options OPAL-RT can provide, as well as a general idea of how the technology can be used to have a successful HIL program at your company. I've included some links to help you continue to learn about the features of the Power Electronics Add-on, as well as who you can contact if you wanted to discuss more with an OPAL-RT engineer. Thank you for watching, and have a great day.